In this video, I'm going to look at problem 35 from chapter 25. 35-35. So this is about power, and it's very hard to ask a non-trivial question when it comes to electric power. So I think this question is doing a good job without introducing any superfluous complications to the problem. So here we have an electric power plant that produces electricity at a fixed power P. So we have something that produces power at P from two terminals, and this electricity is then carried to our household, and so there's of course some resistance over here. Right? Now this power plant is always producing at power P, but they're free to choose the potential difference at which they can actually produce the power. And the book is using V, but I'm going to use delta V to emphasize that this is actually a potential difference rather than a potential. So this electricity is carried as an electric current I through a transmission line of resistance R. So this is going through some transmission current, transmission line of resistance R. Now, strictly speaking, of course, you need to look at the resistance of both parts of this transmission line, but we can easily assume that this is R1 and this is R2, and it's just their sum adds up to R. So we're just going to say that one part doesn't have any resistance, the other part has some resistance R, for simplicity. But we could just say, the resistance is divided into two parts. The user provides the user with electric power P prime. So here, some power is lost through this resistance, through the transmission line, and only P prime is produced over here. And they are asked to show that the reduction in the power, delta P prime, is due to transmission loss given by delta P square R V square. So delta P, which is defined to be P minus P prime, is P square R by V square. Right. Square R being the resistance of the transmission line. Okay? And again, I'm going to call this delta V squared, rather than V squared. Okay? So how do we approach this problem? Now, we produce some current and some potential difference delta V, and this corresponds to some power. So that power is going to be I times delta V, and this is going to produce some other power over here. So presumably there's going to be some different potential difference at the household, or at the electric junction outside your house, or something like that. Let's call that there's going to be some delta V prime over here. So P prime is I times delta V prime, right? This I must be constant. Whatever lets the power company here has to re-enter the power company, so it has to pass through the consumption location. Okay. And we are going to look at the difference between these two. So let's also attach some resistance to where the consumption of power takes place, just to make things a little bit easier. This has to drop out somehow, but for convenience, we are going to just introduce it at this point. So the total resistance in the circuit is going to be R plus R prime, and we can rewrite our power in terms of those. Okay? So we can say that this is I delta V. So this I is going to be delta V divided by, no, I don't like this. I don't like this. So I'll go the other way. So the cancellation is going to be better. So this is I, and this is now I times R plus R prime. Okay, so this delta V, that is the total potential drop across this, must be the current times R prime plus current times R, okay, or the total resistance times the current. Whereas this one, it needs to be I, the current, times just R prime. Okay. So I wrote it this way, so when I subtract these off, there's going to be a nice cancellation. Of course, you can do this a little bit more complicated. The cancellation should still take place. So if I divide these side by side, my delta P is going to be I square. The R prime I square is cancelled. I'm left with just R. Okay. Now, this is what I'm looking for. Is this I P times P divided by delta V? Yes, it is, because P is in fact I times delta V, and hence I is P divided by delta V. If you can substitute this over here, you get P square by delta V square times R, which is what we were looking for. Okay? So there's a follow-up to this question. In part B, they're asking, in order to reduce power losses during transmission, should the operator choose delta V to be as large or as small as possible? Well, as large as possible, right? Because the power loss is inversely proportional to the potential difference that's produced at the power plant. So you should produce this potential at very large potential, this electricity at very large potential difference, and then transmit it. And then, hopefully, over here, you are going to reduce it to the regular household voltage, and then you're going to have very little power loss due to these transmission lines. Okay, so this is actually the reason why we have these high voltage power transmission lines, because if you don't have high voltage, then the power transmission is going to be significantly larger. And this is why the alternating current is preferred over direct current. It's very easy to change the potential difference provided in alternating current by changing its frequency, but this will be very, very hard to do with the direct current. Okay. Right, so that's all.